Alrighty, so we are now moving on from kinematics into the next chapter of physics, which is on Newton's laws of motion. Now, what you're going to find as we progress through this semester is that it's almost like physics or being able to solve problems is broken up into different styles of problem solving. So we just went over kinematics. That's one style. There's a certain class of questions that can be solved using kinematics. And there's, thousands and thousands of problems. But to solve those problems, we're using a certain technique, a certain set of equations, and that's what kinematics is. Now what we're going to do is say, okay, let's forget about kinematics for now. We're going to have to understand stuff from kinematics, like what is acceleration and things like that, and vectors. But we're now going to try to solve problems using a different technique. So instead of using kinematics equations, we're going to be using a different set of equations. And we're going to be thinking about the problem in a slightly different way. This is going to continue because once we're done with Newton's laws, you're going to find the next thing we're going to do is energy. And again, it's almost like we're starting all over again, a whole new set of equations, a new way of thinking about the problems, and those problems will be solved using that technique. So just be prepared that when you get Newton's law type problems, you're not really going to be using any of your kinematics stuff anymore, at least not the equations. Some of the concepts are still important. Knowing how to solve algebraic equations is still important, but you're going to find that it's a new set of equations. Some new terms are going to come up, and that's just the way it is. So, let's discuss Newton's laws of motion. So Isaac Newton, back in the 1600s, came up with, basically a way of thinking about the universe, the world, the physical world. He took ideas from previous scientists like Galileo and Copernicus and a bunch of others and basically drafted what we know of as physics, at least classical physics, the physics before things like quantum mechanics and relativity, which are fairly modern concepts. But he, Isaac Newton, basically developed physics as its own field, separate from what other sciences were at the time, developed it into a very strong field, rigorous, certain sets of equations, certain rules were true, certain laws were found, and we find that they're obeyed by the universe. So, a very important figure. He didn't just come up with these laws of motion, which we're about to discuss. He came up with a whole bunch of stuff. He came up with optics, how light works, how reflection happens from a mirror, color. He came up with thinking about light in a different way than anybody had prior to him. He thought about light as little particles rather than as waves. And even after him, most scientists believe that he was wrong, that light is a wave, and in fact a whole framework of optics was developed in electromagnetism, it's called, for a couple hundred years. All trying to prove that he was wrong in his way of thinking, and it seemed that based on these principles, he was wrong. It was dumb to think of light as a particle. But then comes Albert Einstein, and in one swift motion, he says, actually, Isaac Newton was right the whole time. We have to think of light as a particle. And of course, there are some nuances there. We now think of light as both a particle and a wave, something which has those two characteristics. And so, 400 years ago, Isaac Newton predicted something which is what we now accept to be true, even though all the scientists at the time felt he was completely incorrect, and even for hundreds of years afterwards thought he was incorrect. But we're not going to go into the other branches of physics he talked about. We're just going to talk about the mechanics, the motion. And basically, we need to discuss 3 laws of motion which he developed. The first law says that an object in motion will stay in motion, or an object at rest stays at rest, unless it's acted upon by an outside force. Okay, that's what it says. So I'll write it down. An object in motion stays in motion. Not only does it stay in motion, but it stays in motion at the exact same velocity, constant velocity. So if something's moving at 10 meters per second, it will keep moving at 10 meters per second. Not that it'll just keep moving, but its speed can change. No, it'll keep moving with exactly the same velocity it had. And an object at rest stays at rest unless acted upon by an external force. Okay. So do we see that in real life? Let's say you have your tabletop, your pen or pencil is sitting on a tabletop. If you push the pen or pencil, it'll start to slide across the table. Does it keep sliding forever and ever? No, obviously it comes to rest, unless you hit it too hard and it flies off the table. Let's say you're in your socks and you run and you slide across a hardwood floor or a tile floor or something. Well, you slide for a little bit, but eventually you slow down and stop. In fact, we see this with everything. You kick a soccer ball, well, the soccer ball will roll for a while, but eventually it'll come to rest again. So, observationally, we don't really see it, but it is actually true. And the reason it's true, yet we don't see it, is purely because when we're trying to observe this principle, there are effects which we have to take into account. And that is what the last part of this statement says. An object in motion will stay in motion with constant velocity unless acted upon by an external force. So, when you kick the soccer ball on the field, and it's rolling along, but slowing down and eventually stops, the reason it stops is because there must be an external force. And there is an external force, of course. It's friction of the grass on the ball. When you slide on the floor, same thing. There's friction between your feet, your socks, and the floor tiles. So, in order to see this principle in action, at least the first part, you have to be in a system, in a regime where there is no external force. And that's pretty hard to do. For instance, let's say, okay, let's take a day, there's no wind outside, you go outside with a ball, you throw a baseball straight up in the air. What happens? Well, the baseball goes up in the air, slows down, reaches the maximum height, and it starts to come back down again. So if we take the first law of motion to be true, one would say, well, once you threw that ball up, the ball should continue rising up at constant velocity forever until something pushes on it. But when we look, obviously it slows down, so the speed changes, so there must be an external force. What's the external force in that situation? Of course, it's gravity. We don't see gravity. All we can do is see its effects. But nonetheless, we know there must be some force, called gravity, acting on the baseball. Because if there weren't an external force acting on the ball, then it would have just continued to go up forever and ever. The second part is basically the same statement, except if an object isn't yet moving, so its initial velocity is 0, then it should stay at 0 forever and ever until something pushes it. So obviously you have a glass of water on your table. It's just going to sit there forever until someone moves it, picks it up, pushes it, whatever. So that's what the first law says. It's pretty intuitive. Once we understand that when we see instances where it doesn't seem to be true, we have to go and investigate and see, are there any external forces that may be invisible to us? Then all of a sudden we notice this actually works. And in fact, there's never been an instance where this first law didn't hold. In every situation, ever observed, ever measured, this first law holds. Now there's a second law, Newton's second law of motion. This is a very special law because unlike the first, it's really not a definition or a statement. Really, it's more of the mathematical equation which represents the first law, I'm sorry. So the first law says, an object in motion stays in motion, or an object at rest stays at rest until acted upon by an external force. What does that mean? That means an object will have a constant velocity until a force acts on it. Once a force acts on it, then its velocity must change. Well, what's a velocity changing? That's called acceleration. When an object's velocity changes, we say that object accelerated, sped up or slowed down or whatever. So, the first law, deep down, all it says is that forces change the motion, change the velocity of objects. So the second law is the equation, which says F, the forces acting on an object. In fact, the fancy way is to say sigma. This Greek letter, sigma, means the sum of. So there may be multiple forces acting on an object. If there are multiple forces acting on an object, you add all the forces up. And what does it say? It says whatever that is, that's equal to the mass of the object, which is basically a measure of how easy it is to move the object. It's kind of like weight, but not really. It tells you about the weight of the object, but the weight of the object is different. It depends on gravity and all sorts of things. The mass is something inherent to the object. The bigger the mass of an object, the harder it is to move the object. Objects with smaller masses move much easier. Okay? So, adding up all the forces tells you the mass of the object these forces are acting on times the acceleration of that object. Okay? So we have force is mass times acceleration. Okay. So force, the units of force is what's called a Newton, capital N. But it's really a combination of a whole bunch of units. The Newton is a symbol which basically combines other units together. And those units are kilograms, which is the unit of mass, times meters over seconds squared. So the unit of force is a kilogram meter per second squared. But instead of having to write that every single time, we just say it's a Newton, in capital N. Okay. M, or mass, the unit of mass is kilograms in a metric system. And acceleration, we've seen before, is meters per second squared. This is going to be one of two big equations we use for this chapter. Only two equations, really, we're going to have to know to solve all the problems for this chapter. This is one of them, F equals ma. It's one of the biggest equations in all of physics. And it's really easy. If you want to know how an object's motion changes, that is, if you want to know the acceleration, all you have to know is, well, what object are you talking about? That's the mass. And what are all the forces which are being applied to the mass? Add up all the forces, it tells you about the acceleration. What else is important? This equation is a vector equation. Vector equation. And so just like with the kinematics equations, they were vector equations as well. That means when you write this equation down, you have to be talking about either the x direction or the y direction separately. So if you have an object that has a whole bunch of forces acting on it, some are pushing up and down, some are pushing left and right, then really what you have to do is set up an F equals ma equation for all the left and right forces, and that'll give you a left and right acceleration. And then also set up a F equals ma equation for all the up and down forces, and that'll tell you about the up and down acceleration. Okay. So F equals ma really stands for multiple equations. One in x and one in y. All right, that's the second law. What's the third law of motion? The third law of motion says that anytime a force is applied to an object, then that object must apply the same force back. Right? The wording most people have heard of is for every action, there is an equal and opposite reaction. Okay? So, let's say you're sitting in a chair. When you're sitting in a chair, there's some amount of weight. Your weight is pushing down on the chair. So gravity's pulling you down. That force which gravity pulls down on you is called your weight. That weight is being applied to the chair. The third law says, well, because your weight is pushing down on a chair, the chair must be pushing back up on you with the same amount of force. Because let's say it didn't. If you're pushing down on a chair with all the force of your weight, and a chair didn't push back, then you'd be falling straight down through the chair. The only reason you don't fall through the chair is because the chair pushes you up, keeping you from falling. How hard does the chair push? It pushes on you with whatever force you're pushing on it, which in this case would be your weight. When you lean on a wall, same thing. Some amount of force is applied to the wall. You don't fall through the wall because the wall pushes back on you. How much does it push back on you? It always pushes with exactly the same force that you pushed first. That's what equal and opposite means. You push on a wall, let's say you have your right hand on the wall, so you're pushing to the right. Well, the wall pushes to the left, so that's opposite, and it pushes just as hard as you're pushing. So it's equal and opposite. Same magnitude, same strength, but in the other direction. So those are the three laws of motion. The first and third law are conceptual laws. They help you understand how a system should work. They're the things that should be common sense in your mind for when you think about the motion. You can understand, okay, this is how it should work. I would imagine the ball is going to go up like this and move like this or whatever. But it's the second law, F equals ma, which will allow you to solve problems. You'll actually calculate things with that one. So that's the big one. So let's look at an example. Here's a nice example. We have a floor, nice horizontal flat floor. On the floor is a box. The box has a mass of 10 kilograms. You pull on the box with a rope with a force of, let's say, 50 newtons. Question is, find the acceleration of the block. Okay, nice easy question. There's a block on top of the floor. Let's say there's no friction or anything on the floor. There's a rope attached to the block. You pull on the rope perfectly horizontally, applying a force of 50 newtons. You want to know, how will this block move? What acceleration will the block have? Okay, well, now what we know is we're not in kinematics land anymore. The reason we know we're not in kinematics land anymore is because we have a problem which involves forces. Notice when we were doing kinematics, we never spoke about forces. In fact, the closest we got was gravity, but we said we're going to treat gravity like it's an acceleration. So we never ever talked about forces. Here, all of a sudden, we have a problem which has a force in it. This problem has a force. I'm looking for an acceleration. That's telling me use Newton's second law, F equals ma. All right, so that's what I'm going to do. The sum of the forces equals mass times acceleration. There's my equation. Now, before I would use it, I want to show you a technique that you better get in the habit of using. I say you better, not because I'll take off points or anything if you don't, but rather because as you get more and more complicated systems, it's going to be not quite as easy to tell what are all the forces, which forces do you have to worry about, which ones do you not, all that kind of stuff. So, what I'm about to show you is called a free body diagram. It's basically a picture that you draw which allows you to see all the forces acting on an object. Once you have that diagram, then it's easy to just plug in or take out which forces are necessary and plug them into your equations. So let's look at the picture. What do we have in this system? There's a block sitting on a table. That block has a rope, and a rope is pulling on the block with a certain force. So I want to draw a free body diagram. Okay, well, the way we do it is let the block be represented by this dot. Now I want to draw all the forces acting on that block. Well, of course, I've got one force. Call it F1. is 50 to the right. Do I have any other forces in this problem? Technically, I do. Gravity is always acting in these systems. So I know there's some amount of gravity pulling down. Call it Fg. That's the force because of gravity. Gravity's trying to pull this block downwards, always. Is there any other force? Well, there better be another force, because I know this block is on the table. Anytime you have an object on a surface, then there's going to be what's called a normal force. Normal force is a very important topic. It's going to be more important a little later on, but I'm going to introduce it now so you'll know it for when it comes up. First thing to note about this force, called the normal force, is what does the word normal mean? Well, when I ask that question, I ask it in a scientific terms, like physics and math. I don't mean psychiatrically, I don't mean in our everyday lives. Normal, of course, has a certain meaning that we talk about regularly, but in science and physics, normal means something completely different. Normal means perpendicular. I believe the mathematicians made this up. Why they use the word normal for perpendicular, who knows? Why don't they just use perpendicular? I don't know. But they don't. Well, sometimes they do. They actually have multiple words for perpendicular. One of them happens to be normal. So when we talk about normal force, what we mean is a force which is perpendicular. Well, the obvious question then is, perpendicular to what? Well, the answer is, a normal force is that force which is perpendicular to the surface. So look at our block. There's a surface, the floor, which is horizontal. A normal force is going to be a force which is perpendicular to the floor. So that means the force is going to be up and down. Okay, we now know the direction. It's either up or down. Which should it be? Well, it should be obvious. Gravity is pulling me down, trying to pull me down through the floor. But I know the block's not going to push through the floor. So, I already know Newton's third law says for every action there's an equal and opposite reaction. Gravity's pulling me downwards, but I can't go through the floor, so the floor must be pushing back in the opposite direction with an equal force. So the normal force for this problem is the force because of the ground stopping me from falling through the ground. So here it is. Normal force. Gravity's pulling me down. The floor won't let me move down, so the floor is pushing up. How hard does a floor push up? It pushes up as hard as gravity is pulling me down. That's equal and opposite reactions. All right. Any other forces in my problem? Well, there's no friction, no air resistance. I've got gravity pulling me down, the normal force from the floor stopping me from falling, and then I've got you pulling the block to the right. So there's three forces in this problem. That was the hard part. For every problem you do in Newton's laws, finding this free body diagram will always be the most important and the most difficult part. That doesn't mean it's difficult. In fact, almost always it's easy, which means the rest of the problem is going to be even easier. But it's definitely the most critical. If you don't get the free body diagram right, it's going to be difficult to get the problem right. On the other hand, if you do get the free body diagram right, then it's almost impossible to get the problem wrong. So you need to practice a lot in drawing these little free body diagrams. If you don't like drawing a separate picture like I did here, you can always draw it on the original picture. So you can say, okay, well, there's some gravity here, the normal force is here, and then the force is already drawn. So there's all the forces on the picture. Technically speaking, if you have a professor who's really, really strict about it, you're supposed to draw a separate problem where the object is defined as a little dot. I don't care. From now on, you're going to see when I draw the forces, I draw it on the picture because I'm lazy. And if you want to do it that way, that's fine too. Okay, we now did the free body diagram. We now know what all the forces in my problem are. Now let's read the question. Find the acceleration of the block. All right, well, ask yourself this question. In which direction will this block move? And when I say direction, I mean x direction or y direction, or both. Well, I don't think the object can move in the y direction because the floor is there. So obviously the block can't move down through the floor, and it can't move up because there's nothing pulling up on me. The normal force is there pushing up, but all that does is balance gravity. It can't be bigger than that. It has to be equal to that. So when I look at this, I say, well, the only external extra force sitting there is my applied force, the force that's pulling on the block to the right. So because of that, I know I only have to look in the x direction because that's the only direction that the acceleration is in. So when I use F equals ma now, all I worry about are all the horizontal, all the x directional forces. All the y directional forces, I'm just going to ignore because I don't care about them. So let's do it. In the x direction, I have sum of the forces equals ma. What are all my x forces? Well, I've got my applied force, 50, and that's it. So those are all the forces added together, equals ma. Now I plug my numbers in. 50 equals m, 10 kilograms, times a. And now I just solve this for a. Divide the 10 over, I get a is 5 meters per second squared. So obviously, really easy. No big deal at all. I have an object or a system. I say it's a system. The system is basically one object. It's sitting on the floor. I pull on the object with a certain force horizontally. Gravity is involved. There's a normal force somewhere. I draw my free body diagram. I then say, in which direction do I need to look? Well, the question's asking me about the acceleration of the block. My intuition tells me the block has to move in the x direction. It can't move in the y direction. So I only have to do F equals ma in the x direction. Since I'm only doing it in the x direction, I only care about x directional forces. In this case, there's only one. So F equals ma is 50 equals 10 times acceleration. And solve for a. Let's try another. Of course, a little bit more complicated. Here's our floor. Here's our block. Again, mass of 10. This time, I'm going to push on the block with a force of 100 newtons. And someone else is pushing back, F2, 1 and F2, of, let's say, 25 newtons. Question says, find the acceleration. All right. Well, before I calculate, let me go ahead and draw the forces that are on this problem. I've already drawn the two applied forces. I also know gravity is here, Fg. There's a normal force. The normal force is always perpendicular to the surface. The surface is horizontal, so the normal force must be vertical. And in this case, it balances gravity, so it has to push upwards. No friction, so no other forces. Those are all the forces in my problem. Then I ask myself, what's the question? Find the acceleration of the block. Okay. Well, which direction is this block going to move? X or Y? Or both? Well, it's not going to move in a Y direction because nothing is moving it up and down. So I would assume it must move in the X direction. So looking in the X direction, I use the equation F equals ma. So now let's do it. What do I have? Well, I've got F1, which is 100 pushing to the right, so I call that positive. And then I've got 25 pushing to the left. To the left is negative, so minus 25. I don't care about any of the Y forces, so these are the only X forces. Set it equal to mass, 10, times acceleration. And there we go. Here's my equation, solve for A. So of course 100 minus 25, that's 75, equals 10 times A. That tells me A must be 7.5 meters per second squared. So very similar to before, only now I have multiple forces, which means I have to add all the forces together. But because they're vectors, I care about the directions. I'm using the standard. Anything which goes to the right is positive. Anything to the left is negative. So I have 100 newtons to the right, that's positive 100, plus 25 newtons to the left, that's negative 25. Add them together, I get 75. Divide by the mass, gives me acceleration. All right, let me do one more example. And this is where we really have to be careful and where problems can actually start to crop up. Here's my floor. Here's my block. 10. Let's say I have F1 is 100. And then I have F2 is 20, but it points at an angle of 30 degrees above the horizontal. Okay. All right. Well, what's the question? Find the acceleration. All right. Well, before I worry about that, I want to go ahead and look at all the forces in my problem. Number one, there's no friction yet. That comes later. There's gravity. There's always gravity, pointing straight down. And then there must be a normal force. The normal force is always vertical. And what do I know about it? It has to balance all of the other vertical forces. So it's always perpendicular. That told me vertical. The other thing I know about a normal force, which we will see, is that it has to balance the rest of the forces in that direction. So there's some amount of F2 which points up and down, and of course gravity points up and down. You don't have to worry about it now because we don't actually care about it, but I can tell you the normal force is going to point up in this case. Sometimes it might not. Sometimes it might point downwards. It all depends on what all the other forces look like. But when it comes time to worry about that, I'll show you how to figure it out. For now, it doesn't matter. I just want to be consistent in showing you, writing down all the forces. What's the next step? Well, before I worry about solving the problem, I see something unique here that wasn't in my other examples. And that is, I've got a force which is pointing at an angle. And just like with kinematics, I said, if you ever see something in an angle, the very first step should always be to break that thing up into x and y components. So that's what I'm going to do here. I have a force F2 that's in the angle direction. So I want to break it up into x and y components. Here's the x side, there's the y side. So F2 needs an x piece, and F2 needs a y piece. Well, by now we should have some experience with this. I want the x component of F2. That side is the side adjacent to the angle, and adjacent goes with cosine. So F2 x component is 20, the actual force, times cosine of 30, which is 17.3. The y piece, the y side is the side opposite to the angle, so it's going to be 20 sine 30, which is 10. And then if there were other forces at angles, I would do the same for those forces. Every single force which is at an angle, break it up into components first. And you'll have them all listed down. The reason you do that is because when it comes time to do your equation, all you want to have to do is take the information and plug it into your equation. So up front, you do all the work, all the thinking, and all of that. Once that's done, solving the algebraic equation should be just like cranking a machine. You take the numbers from wherever you got them, and you just plug them in, and you get your answer. So here we go. We had an angled force. Break that force into its x and y components, and now the information is just sitting there for us to use. Now that that's done, we can look at answering the question. Find the acceleration. So again, I say, which direction is this block going to move? Obviously, because the floor is underneath, it has to move in the x direction. So again, I'm looking in the x direction to solve this. What's my equation? F equals ma. The sum of all the forces in the x direction must be the mass times the acceleration. So what are all the forces in the x direction? Well, let's see. I've got F1, that's 100, which points to the right. Then I've got F2, which is at an angle, but I calculated the x piece already. The x piece was 17.3. Did that piece point to the left or to the right? Well, F2 points up and to the right, so obviously the x piece points to the right. So he's also positive, and he's 17.3. What about this 10, F2y? How do I plug the 10 in? I don't care about the 10. The 10 component of F2 is in the y direction. I don't care about any y forces. All I want are the x forces. So this is it. These are all the forces in the x direction here. So equals mass times acceleration. So 117.3 equals 10 times A. A equals 11.73. And there you go. Here we had an extra complication in that one of our forces happened to be at an angle. But because we focused so long at the beginning of the semester on x and y component stuff, we know how to handle it. Take whatever force is at an angle, Give me the x component and give me the y component. Now when I go to use my equation, I have to look in either the x or the y direction. In this case, the x, because that's the way the box is going to slide. So all I have to do is take all the x pieces. All the y's, I just ignore. And that's all there is to this stuff. Obviously, things are going to get slightly more complicated when we talk about friction. But this is the basics. And this is actually 75% of everything you need to know for Newton's laws. So if you know how to do this, if you can break in things into components and do this F equals ma, then you're well on your way to doing everything you're going to have to do for this chapter. The rest of the problems that are more complicated won't really change how you solve the problem. You're going to use these steps. It's just you have to be sure you know which forces to break into components. You know which forces you can use in your equation. Are you looking in X or are you looking in Y? So I think that's it for now. That's enough of the theory. I hope it's understandable. Of course, I'll be making another video soon with some more example problems. And then we're going to move on to friction and see how adding friction into this process affects how we solve the problems. And you're going to find it only adds one extra step, really. So that's good news. All right, so please go over this, practice these, look on Canvas for the practice problems. And if you have any questions, of course, feel free to email me and ask me. But until next time.